So this video is going to talk about partial sums for sequences. The reason it's called a partial sum is because when we're dealing with a sequence, you have an infinite number of terms, and while some very specific sequences have a complete sum, literally if you add up every number in the sequence, which is weird when you're talking about an infinite value, but the sequence actually does equal something when you add up all the digits. Most of the problems that we're dealing with don't fit that category, and so we're doing what's called a partial sum, which means we're just going to look at one chunk, one series, one part of the sequence, I guess I should say, to find its sum. So let's talk about some notation here. Sorry about all that. All right, so this is telling you to do a sum. This is the Greek letter sigma. It is used as summation. All right, so that's the first thing you want to know, is that you are dealing with a sum. This is the expression that we are going to be working with. The number at the bottom here tells you where to start, and the number at the top tells you where to stop. I don't know why I just tried to spell stop with an E at the end of it. I don't know. Okay. So remembering that n is your term number, if your start and your stop numbers are relatively close together, you're just going to list out the values. So we've got our first term, our second term, third term, fourth term, and I'm going to stop because that's my value at the top to stop. And for each one of these, I am told to take n, right, n, and multiply it times 3. So 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9, 4 times 3 is 12, and to find the sum, I am going to take these 4 values, and I'm going to add them together. So 3 plus 6 plus 9 plus 12 equals 30. That's not hopefully too bad. There was a hopefully in there. Again, a few different things. This is the value you're starting with. This is the value you're stopping with, so 1, 2, 3, 4. And this expression is what you're asked to do with each of those numbers, okay? Once you've got those values, this is a small enough sequence, it's not too bad to find those, just add them up. That's what sum means to do. Let's take a look at problem number 2, see if we can follow that same type of patterning. So we have a sum again. This time, though, our expression is 2 to the n power. N is equal to 1 as our start. N is equal to 5 as our stop. I keep trying to put extra letters at the end of stop. There we go. So a couple of different ways. Keep track of this however you want to. If you just want to write out, okay, I can do 2 to the 1 in my head. It's 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. And 2 to the fifth is 32. It's up to you how you keep track of this. And at this point, take 2 plus 4 plus 8 plus 16 plus 32. And when you add those up, you get 62 as your final answer. Now, if it helps to remind you how you got these values, this was 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and then 2 to the fifth. So you start with 1 here, stop with 5 there. So as long as the numbers, again, aren't that far apart from each other, this isn't too awful. Even if this had been, let's say, n is equal to 10, and if this was n, stop at 15. From 10 to 15, still dealing with a reasonable number of n values to work with. So let's take a look. Now we've done 1 and 2 at number 3 here. Okay. So again, we're dealing with a summation. Our expression here, every n value, we're going to subtract 3 from it. And we are going to start with 1. You do not have to start with 1, so be careful that you're paying attention to that start value. And your stop value here is 7. So there's not that many numbers, so if I look at this as, let's start with 1, so 1 minus 3 is negative 2, and 2 minus 3 is negative 1, 3 minus 3 is 0, and I'm going to keep going all the way up to 7, so 1, 2, 3, 4 minus 3 is 1, 5 is 2, 6 is 3, and 7 is 4, right, 7 minus 3 is 4. In between each one of these, remember we are adding, this is summation, so add them all up. And this sum is equal to 7. That's not too bad as long as the sum is relatively small and the start value and end value are relatively close together. Let's say I change things on you just a little bit. So I'm going to take that same summation. I'm going to say that n is equal to 1. Not too bad. I'm going to give the same exact expression, n minus 3. Okay? But this time, I don't want to stop at 70, or 7. I kind of gave away. I'm going to have you guys stop at 70. So you are starting at 1, you are ending at 70, and I don't know about you, but I am not going to list out 70 values of a sequence to then add them up. Even if I wanted to list out all 70 of them, I am bound to make a mistake somewhere. And then when I try and put in my calculator for 70 numbers, again, quite likely I will make a mistake. So what happens if I give you this type of problem and I still want you to find the summation? So it's not as awful as it sounds. What I would recommend you do, and I'll go ahead and zoom in on this, just this piece of it, start writing the sequence. So if n equals 1, your first term would be negative 2. And then if n equals 2, your next term would be negative 1. If n equals 3, you get 0 on down to whatever. Okay? So now I know that I'm dealing with a sequence that's an arithmetic sequence. So I know my d value is 1. I know u sub 1 is equal to negative 2. And I can use this information to find out what happens for this 70th term. Because off the top of my head, I don't know what it is. Okay? Actually, I do know what it is. There's something else I don't know. I'm trying to remember. No, I got it all. Okay. I'm having a mild issue here with my brain. What I do know, 70 is where I'm supposed to end for my term number. I actually can just substitute it in to find out where I end. It took me a minute to remember that. So 70 minus 3 means my sequence actually ends at 67. I can remember things some days. All right, so u sub 70 is equal to 67. Now, using our arithmetic sum, so S sub n is equal to n over 2 times u sub 1 plus u sub n. Do a little substitution here. We have 70 terms, so S sub 70 is equal to 70 over 2 times our first term plus our last term. Into a calculator it all goes, and you get 2,275. Now, the reason we knew the last term, and that's the one I got hung up on, my apologies, we knew the last term because we knew what our n value was, and we knew the expression to substitute it into. So the thing that we didn't know was initially, was it arithmetic or was it a geometric sequence? And that will depend entirely on this expression. So if you have a small enough difference here from n is 1 to n is 7, go ahead and write it out. If I give you something like this, n equals 1, and I ask you to go to 70, please don't write it out, all right? I think there are easier ways to do this. Okay. So we have those examples when you are dealing with the summation notation. We have two equations. You have an arithmetic partial sum, which we actually just talked about. So S sub n is equal to n over 2 times u sub 1 plus u sub n. This one doesn't really have much reference in terms of knowing that it's arithmetic, but I think when you see the geometric, you will hopefully be able to tell the difference between the two of them. I'm going to zoom in because the geometric is going to take me a second to write. All right, it is the sum of n equals 1 to k u sub n equal to u sub 1 times 1 minus r to the k over 1 minus r. This has to be set up as a 1. This is your ending value, so you notice this end value is what matches over here. Okay, you know your first term, so u sub 1, and then r, remember, is the common ratio in your sequence, specifically your geometric sequence. Okay, let's do a few example problems and see if we can put this into practice. So problem number 4, we have a sequence of 3, negative 6, 12, negative 24. We're alternating signs, which to my brain basically reminds me that I'm probably going to be multiplying by some negative value, specifically in this case negative 2. And I then know as soon as I said multiplication, we're dealing with a geometric. So the sum of n equals 1 to 7, and you don't have to write anything specific there for this expression because we already have the term, so we're good with that. So this is equal to my first term times 1 minus my common ratio raised to the k power, which is that top value, right, that you're ending at, over 1 minus negative 2. I will tell you right now, these signs do not go well. All right? I've seen way too many mistakes with these signs where students put something in their calculator wrong. They think they can do things mathematically that they're not allowed to. So please be careful, first of all. If you are decent with your calculator, this whole mess can go in as 1. And that's what I'm going to do right now. So we have 3 times 1 minus negative 2. I'm going to raise that to the 7th power. Then I need to take that and divide by 1 minus negative 2 in the denominator. And you should get 129. Now, I would say if you're not terribly confident with your calculator, take a minute, practice with it. Use parentheses as needed, or take it apart in pieces. Do just the numerator here, do just the denominator here, divide them, then multiply times 3. Whatever you do, though, practice a little bit if you need to, and make sure that you're getting that 129. If you're not getting the 129 and you cannot make your calculator work, message me, email me, but get a hold of me so that I can help you out with that. All right. Problem number 5 doesn't look like it has any directions, but it has the same directions as number 4, which means I'm looking for the 7th partial sum. All right. The difference is here, though, to get from 10 to 13 and then 13 to 16, I'm adding 3 each time. So if I'm adding, that means I'm looking at the arithmetic formula. So S sub 7 is equal to 7 over 2 times my first term plus my, I don't have a 7th term yet, do I? Right. If I don't have my 7th term, I need to find my 7th term. So when we did the explicit definition, you can write an explicit definition for this one. So u sub n is equal to u sub 1 plus n minus 1 times d. And fill in everything that we know. We know we're looking for the 7th term. Our first term is 10. N is 7 minus 1. Common difference is 3. So u sub 7 is equal to 28. I know that's now 28. So my first term was 10. My 7th term is 28. Let's see what we get here when I calculate all of this fun stuff. So 7 over 2 times 10 plus 28 gives us a grand total, a partial sum of 133. Geometrics will add up very quickly, although in this case, because we were in problem number 4, we were alternating signs. So for every positive number, we added a negative, keep going back and forth. And so it depends with that one. Problem number 5, though, everything was positive, so it should increase nicely there. Number 6 and number 7, you're asked to find both a term and a partial sum. Let's zoom in on 6 here and see what we've got here. All right, 9th term. Let's start with that one. I think we've actually seen this sequence before, and that's okay. 1/2 to 2, then 2 to 8, 8 to 32. That is times by 4. So we're talking geometric here. So u sub 9 is equal to my first term times the common ratio raised to the n minus 1 power. So 4 to the 8th and then times 1/2, 32,768. That's that exponential growth kicking in there. And then we have the 9th partial sum. We already know it's geometric, so to do the 9th partial sum, I've got n equals 1. I'm going to go to the 9. U sub n is equal to my first term, 1/2, times 1 minus 4 to the 9th over 1 minus 4. Practice, 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 what I'm going to keep saying, right? You are not going to know how to do these unless you've done a few of them. Okay. And I'm putting it in my calculator right now because there's some things I can do in my head and there are things that I can't. And trying to figure out 4 to the 9th, that's going to fall into the Miss Curran cannot do that category. 43,690.5. That is your 9th partial term. Partial sum. That's what I'm looking for. Partial sum. So if we take this sequence, we wrote out 9 terms and we added them all up, this is what we would end up with. And your 9th term is sitting right here. So with partial sums, especially for geometric sequences, one of the things you'll notice is that the term numbers aren't going to be terribly, terribly large because it's exponential growth and your numbers grow just too fast at times. All right, so let's take a look at number 7. The last problem on this page. I'm looking for the 100th term. I'm going to take a guess that this is going to be an arithmetic sequence. And then we're eventually going to find the 100th partial sum. 100th term here. U sub n is equal to, well, I know I can do this one, but let's see. 3 to 5, 5 to 7, that's adding 2 each time. It's 100% arithmetic. So let's do the 100th term minus 1 times 2. Whip that all into a calculator, and you should get the 100th term to be 201. Now I want to find the 100th partial sum. So the sum sub of 100 is equal to 100 over 2 times my first term, which is 3, plus, I don't have my 100th term. So I'm going to take a break here for just a second, and I am going to find u sub 100 by using the explicit definition. So 3 plus 100. I need to stop doing this for a second. Okay, back up. For anybody who is, yelling at the screen, you have found the 100th term. It's right here. All right. I'm so glad this is almost done because clearly I'm just making more and more mistakes as I go. All right, guys, I'm sorry about that. So we knew the first term. It was given in the sequence. We figured out the 100th term already. I just needed to remember to use it. Okay, all of that goes in a calculator. I promise I can make my calculator work. All right. 10,200. Okay. I really hope this has helped, and I hope my mistakes have not been too distracting. I'm sorry about those. Guys, ladies, if you are working on these problems, hopefully the video has helped. If you have any questions, you know where to find me. Send me some questions. And I promise, well, I'm not going to promise, but hopefully the next video won't have this many errors in it. All right.